Hello everyone, in this video we are going to visualize the electric field using the geometry nodes in Blender 4.5. This is really a cool effect, and in this we're going to also explore the parallel loop method that run the calculations in parallel, and it is really fast. So let's get started. So first I'm going to explain the concept and then we're going to build the node tree for this. So we're going to do calculations in 3 steps. So first we're going to calculate the electric field for one charge and one position, like in this case, and then we're going to do that for multiple charges and one position, and later we're going to do that for the multiple charges and multiple positions. Okay, so let's say we have this charge q1 and then we have this position p1 where we want to calculate the electric field due to this charge, and the p1 is at r distance from this point. Calculate the electric field, we can use the Coulomb's law. So in this formula is the electric field K is constant, we can treat that as 1. Then we have to specify the value of the charge of this and divided by the distance square, and then we need to multiply that by the r cap. R cap is basically the normalized vector of this distance vector. Okay, so let's first do this. We're going to add a plane and then we're going to add the geometry nodes. So let's first add the distribute points node to add the charges, and here we're going to use really low value so that we have only one charge, something like this. Let me also add a frame. So this is our charge or charges. Next we need to store the value of charge, so add the store named attribute node and type here charge, and here we can specify the charge value means 1 or any other value. 1 is positive charge, -1 is negative charge. Okay, and later I will show you how to randomize this. So let's also add the symbol to these charges so that we can understand this properly. So when the charge is positive, we're going to add the plus symbol, and when it is negative, we're going to add the negative symbol. So let me create that. Now we have these icons for the charts. So let me hide that and bring this. So let's also add that here and separate the children and add that to the instance. See, now we have this plus symbol, but later we're going to have multiple type of charges, positive or negatives. So we need to specify the instance index. So change that to pick index, and then we're going to add the switch node. Here we're going to add the named attribute node and then select the charge attribute. When it is positive, we're going to add the instance index 1, and when it is negative, we're going to add the instance index 0. Okay, let me show you this. See, we have 1, and if I change that to negative, we have 0. So that is really important. So now if we visualize this, we have something like this. If I change the charge value, see, we negative, we have positive. So let's put this in a frame. So now we have the charge symbols. Okay, so next we need to add the position point. So let's add the point, a single point. We have this point. Let me put that at this location, and let's also combine that with this. So next we need to sample the position of this point so that we can calculate this r vector. So let's add the sample index node, change that to vector and type here position. Now we have the position of this point at the location of the charge. Let me show you this. So this is the position, which is 220. Now we have at the charge location. So next we're going to add the subtract node, and we're going to subtract the position of the charge. So that will give this r vector. Okay, so next we need to normalize this so that we have that r cap vector. So this is the R cap, this one, and also we need the magnitude. So let's calculate it is length. Now we have this length of this R vector. Next we need to add the power. See, it is at the bottom. So we're going to add the power with the -2. So it is basically something like this. We multiply this together, then we're going to divide this by 1. Basically, we are doing these two operations in single operation using this power option. Okay. Now we have this, and next we need to multiply this by the charge and the named attribute node and specify the charge. And after that, we need to multiply this into the R cap. So we're going to add the V scale, and then we're going to add that as a scale. So now we have this electric field. So next step is we need to transfer this electric field from this charge to this position. Okay. So why we are doing this, like we are bringing the position of this point at the charge, then calculating the electric field and then transferring back to this position. This is basically for the parallel loop. You can also use the double loop, another concept that I have explored, and I find the parallel loop is the fastest one. If you are interested in other concept, you can get the project file from my Patreon page. So now we have this electric field, and next we need to add the sample index node. We're going to sample this electric field from the charge for this point. Okay. See, now we have this electric field at the point location. Now we have many possibility to visualize this electric field. We can visualize using the color, we can attach a arrow, or we can visualize that using the lines, the electric field lines. Okay. So for the electric field lines, the first step is we're going to add the set position node, and then we're going to normalize this electric field. Okay. Because we are only interested in the direction of the electric field, not the magnitude of the electric field. Then we can add the scale node, and we can slightly push this point in the direction of the electric field. 0.25, and let's see. So we have, this is before, this is after. So now we have new position, and then we're going to repeat this whole process for this position, and we will get the electric field, and then we can further push this point. So if we combine all these points, we can basically create a electric field line. Okay. So for that, we're going to use the repeat zone. So let's input this point into this, and this should be inside this loop. Okay. And this is also outside this loop, and we have this. So now if I go to the 0 iteration, we have original point, then we push that based on the electric field at a new position. Now we have the point at the new position. We can repeat this process and calculate the electric field and push that further. See, it is moving in the direction of the electric field. But to create a lines, we need to combine these points. So we're going to add the join geometry node, and we're going to join the original point with this offsetted point. Okay, so now we have this. So if we increase the iterations, see, it is working, but there is a problem. If I go to the first iteration, and let me add the domain size node, change that to point cloud. See, we have 2 points, so that is nice. Originally we have 1 point, so 1 point go this way, and that point also go this way, and then we offset that based on the electric field, and after that we combine that with the original point. So now we have 2 points, one is original one and another one is based on the electric field. But if we go to the second iteration, at the first iterations we have 2 points, so now 2 points go this way and 2 points also go this way. So in the end we are end up with 4 points. If we go to the third iteration, we have 8 points, then 16, 22. So that will create a problem. So we need to fix that. The fix is really easy. Basically, we only interested in the latest offset point. We are not interested in the other points. So we can add the store named attribute node, change that to Boolean, type active, and add that flag. Now our input point is active. So next, for this, we need to separate those active points. Add the named attribute node and type here active. So now we are only offsetting the active points, and also we need to deactivate the points that are already offsetted. So we can use the store named attribute node and disable the active flag. So we have 5 iterations and we have 6 points because we have one is original from the input. Okay, so now it is working fine. So we have this active field line based on this charge. We can convert that into the curve using the point to curve node. See, now we have this electric field line. Okay, so with this setup we can calculate this line for one position and for one charge. See, it is working nicely. Next step, calculate the electric field at this position due to multiple charges. Okay, so to calculate the electric field, basically we have to calculate this distance vector for individual charges, and then we can use this formula. Basically calculate the electric field due to the first charge, then calculate the electric field from the second charge and add them together. So that will provide the total electric field at this point P1. So this should be a vector summation. This is called the principle of superposition in electrostatics. So we're going to utilize that. Okay, let's add two charges. Now we have two charges, and then we assign the charge value to them. And if we see that, so this setup is working, but there is a problem. If we see it is electric field, we have two value of electric field. One is for this charge and one is for this charge. But here we are only sampling the one electric field value. So before the sampling, we have to do the vector summation to get the total electric field at this position. So for that, we can use the accumulate node and connect this to the total, not to the leading, not to the trailing, but for the total. And basically this node is going to accumulate or add up this electric field and provide the total value. And you will see for both the charges, we have this total value. So these are the individual values and this is the total value. And now this is working fine. See? So this is before, this is after. And another thing we can do is that we can add the negative charges, add the switch node, then add the random node. Type here negative one, here positive. With this node, we can basically randomize the charge. See, now this line is working nicely. See, it is starting from this positive and then ending at the negative. Okay, now we have calculated the electric field from the multiple charges for a single position, and next we're going to calculate the electric field for multiple positions from multiple charges. Okay, so let's say we have these positions P1, P2, P3, and we have this set of charges. First step is we're going to add or store the index ID to these points. Then we're going to duplicate these group of charges, and we're going to assign the duplicate index 0, 1, 2, 3, and so on. So basically we're going to use this duplicate index to get the position of this point for the first group, and then we're going to use the second duplicate index to get the position of the second point and calculate the electric field, so and so forth. And after that we're going to transfer that back to these positions using the index. Okay, so let's do these steps. First, store this ID and also duplicate the group of charges. So let me add the distribute points node, delete this, and also add the transform geometry node. Okay, let me decrease this to maybe 1. Okay, something like that. And we can push that here. Okay, so now we have these points. Then we're going to store this ID. So let's duplicate the store named attribute node. Connect these, change that to integer and type here p underscore id, and here I'm going to connect the index. Okay, let me also make this iteration 1. So now we have stored this PID, and next we need to duplicate the charges. So we're going to add the duplicate elements node, and it's going to duplicate these points. And nice thing about this node is that it provides the duplicate index. And here we need to define the amount, and amount should be equal to the number of positions. Change that to points and connect that to the amount. If we see this, let me add the set position node. Okay, connect that to the offset, and let me also hide this. See, we have 4 sets and they have their unique duplicate index ID 0, 1, 2 and 3. Basically we're going to use that to pull the position of the individual points. So let's connect that to this. So now it is providing the position for individual sets. So let me show you that. Plug that into this. So we have these 4 sets, and here we have 4 positions. See, and if we see that here, this set get the first position or the position from the first point, this set get the position from the second point, and so on and so forth. We are calculating this electric field. Now there is a problem. Here we are adding the electric field for all the set of charges, but we need to do that for individual sets. So we're going to utilize this duplicate index as group ID. So it's going to add up the field for individual sets. Okay, and that again, let me add the set position node and show you that. And so we have these 4 sets and they have their this electric field, total electric field. So without this ID, we have this. All the points have one electric field, but with this, individual sets have their own electric field. So that is really important. Now we have individual electric fields and we are sampling it and then offsetting the points. And why this is happening? Because we need to specify the group ID. Otherwise, it's going to connect all the points, but we want to connect the individual points that has unique ID. Let me show you this. We add 5. See, these points have a 0 ID. This point has 2, 3, 1. If we specify this curve group ID, then it's going to connect those points. So that is nice. We increase the iteration. See, it is tracing the field line. But there is a problem. All these lines based on the single electric field. If I change the index, see, these lines are changing. So here we need to specify the index. So with this, we are sampling the electric field from the corresponding sets for the points. Okay, so now it is working fine. If I make 25, see, now we have this really nice dipole lines. And let me decrease this scale so that we have nice smooth lines. This is basically kind of integration step, and here we are basically using the Euler integration. And another thing we can fix is that, see, these lines are piling up at the negative charge. We can fix that. First add the delete node, and here we need to specify the selection, and here we can add the KS point wall of node. So this is the part of the extra nodes. So let's connect that to the selection, and here we need to make this 0 and slightly increase this, maybe 0.05. Yeah, see, now we are deleting the points that are really close to this negative charge, and here also we should connect this to this, not the duplicate charges. So now we have this complete setup. You can play with the position points as well as charges. Now let's add a material to this and visualize the charge transition from positive to negative. We're going to add the set material node, and here we're going to add the material, then select that material here. So let me go to the top mode. We're going to add the attribute. So type here charge, change that to instances because the charges are instance, but this is geometry. So we have to duplicate this and change that to geometry and add them together. This is a nice trick. So this will work for both the geometry as well as for the instances. And then we're going to add the ramp node and connect that to the base color. See, let me change that. Okay, so now we have this color for the charges. Now let's also add for the lines. First we're going to convert that to mesh, and here we're going to add the curve circle, or maybe 6. So now we have this geometry for these lines, but we need to specify the charge on these lines. Okay, so let's duplicate this node, change that to float, and we're going to accumulate this value, basically charge that is multiplied by the inverse of distance square. Now we have this value, and then we're going to sample that, and after that we're going to store that. Change that to float, type here charge, and connect that to this. See, we have this, and there is slight problem. See, we have these blue ends on the plus side. That is because we haven't stored the charge to original points. So let's duplicate that, connect this to this as well, and here we need to specify the selection because that should be done only for the first iteration. Okay, so now we have this, and another thing we can do is that we can divide this value, this total value, by the number of charges. So that will give this really nice fall off. Let me duplicate that and divide that by the number of charges. So now we have this really nice transition from positive to negative. Okay, and this is the complete setup. And here you can input any mesh. You can input, let's say we can input the icosphere, and now we have these charges on the icosphere, and we can duplicate this and slightly move these charges inside this icosphere so that we have these open lines. Here you can play with the probability of the positive or negative charges. We have all negatives, we have all positives. And another thing you can do is that you can also move these charges based on the noise or using the wiggle fall of node, maybe 0.0025 for the magnitude. See, now these lines are moving because our charges are moving. So now we have these lines. You can increase the number of position points, maybe 250. So now we have really dense lines. So this is it. I hope you learned something from this video. You can get the project files from my Patreon page, including a file where I explore different methods for the integrations and calculations. I hope you like this work. So if you like, then please like the video and subscribe to my channel for more updates. So thank you for watching. See you in the next video. Happy noding. Bye.